So today we're happy to have Rien Weygaert.
Yes.
Or something of that nature. Visiting us from Groningen. Rien was a citizen a long time ago in the past, but he's been at Groningen for a while. We've done a lot of work on different aspects of large infrastructure, in particular the Cosmic Web. He's going to tell us about something related today.
Yeah, thank you, Simon. I was happy to be asked to tell something about my work, given that I was for a return visit to Canada, and indeed, I was one of your predecessors. I was also, in the time that I was here, a long time ago, more than 20 years, the seminar organizer, so I know how it feels. So what I want to talk about today is the work that we've been doing in Groningen on the Cosmic Web, and some particular aspects. One of these aspects is the morphology of the Cosmic Web by means of an analysis tool that we have developed called Nexus. That's where that name comes from. So it looks both at morphology and topology. But I also want to talk about some of the dynamics that is underlying this. Some of it is very recent work and has made us return to the theory of caustics and catastrophe. That's the second thing that I actually want to talk about. And given time, I want to go to what you see here on the background, which is a reconstruction of the local universe. What you see is here a line, a filament, and that's a reconstruction of the Perseus filament by a reconstruction that uses the Burgers equation and adhesion theory. But it might be that in view of the time we will have to skip that. Now the work that I present is not my own work only. There's a lot of people who have been involved with this. In particular, the people that you see here in the top. In particular, some of my PhD students and former students, Marius Cotin, Job Veldbrugge, Johan Hidding, Miguel Aragon, and Bernard Jones, who was my supervisor. So keep in mind that a lot of the work that was not done by me, but was done by them. So what do we talk about? We talk about the Cosmic Web, and of course a lot of people here know about the Cosmic Web. Actually the name originated here. What we talk about is the structure that we see over here. Right. Now this is a dark matter simulation. It's a large simulation called Cosmogrid, and the first thing that you see is of course that there is a non-trivial pattern dominated by kind of filamentary features as well as underdense regions, and you also see the nodes in the network. And one of the questions that we seek to address is what are the connections between all these things spatially. Now when you see such a two-dimensional thing that doesn't give the whole picture, so it's much nicer to sort of give a three-dimensional view, but of course if you show a whole box then it gets completely cluttered. So a more medical approach would be to show a CT scan. And that's what this movie is going to show. We start at the bottom of this box and we proceed through the box along the Z direction. And as that happens, you see basically the spatial connections between these things. So you see that the underdense regions are not going to keep the same volume. They either become smaller as a void sort of closes off, or they become larger as you sort of go more to the central pieces. Some of the lines that you see here proceed over various slides, and that means that they are not filaments, but they are more planar-like in nature, while other things are only existing in a few of the CT scans. So that's an important feature that we're going to show. But another important feature is that there is no scale in principle. You see that there is features on a whole range of scales, and that's the multiscale cosmic web. When you look in the voids, you see there's a lot of tenuous structure over there. You could actually recognize that within the voids there are even smaller voids, and there's also a lot of smaller filaments. And that sort of gives the theme for the talk today. So you see that some of these things here exist over an enormous range of scales, you see that this void becomes very open as it opens up. And look at the enormous amount of tenuous structure in these things. So we're talking about distinct anisotropic features together with a lot of substructure. And the substructure here is in a simulation, but you can actually also look for it. And we did look into it with a survey of void galaxies that were found in the Sloan survey. And indeed, inside those voids, you can actually find galaxies and find that they are actually quite different than the regular galaxy. They're all tiny blobs. So this is sort of the structure that we want to talk about. Now, whether this is reality or not, well, yes, and I always find this one of the most impressive and interesting pictures that we see. This is actually a reconstruction, the projection on the sky of a reconstruction of the cosmic web in our local universe on the basis of the 2-mass redshift survey. This was made by Francisco Quitaura with a Bayesian inference technique. And what you then get is basically the outline of the cosmic web in the local universe, but in the dark matter that we can't see. So you see, it's a very complex and intricate structure. It looks much more outstanding than what you see in the galaxy distribution. So this is basically on the basis of this probabilistic method, the kind of structure in which we are embedded. This structure is not just something that you see or can reconstruct like this, but it also has a lot of dynamical impact on the environment. And in this sense, I just want to point out a recent publication by Hoffman et al. Pomerado was the first author, based on the cosmic flows 3 map. That's the state-of-the-art sample of peculiar velocities of galaxies in our local universe, put together by Brent Tully and Hélène Courtois and collaborators. And the map by now of the peculiar flows is so good and has so many elements that you can actually reconstruct the velocity field and density field on the basis of these peculiar velocities and start to distinguish the imprint of the nonlinear structures in the universe. So they made this beautiful movie. It's actually taken from a movie where you see the dominant cluster-like and supercluster-like features. They are in red. And you see basically the flow lines inferred from the velocity field in those regions. And you see, for example, beautiful shear flows along what we know are filamentary extensions. So even in the velocity field in the local universe, we can recognize this cosmic web in terms of its dynamical imprint. So that, of course, conjures up why would you be interested in the cosmic web. I always find it very interesting that there are cosmologists who then ask, what's the use of this? Why do you want to do this? And the question, of course, means how do you get omega out, or omega lambda? But I always find it funny that the cosmologist asks, what's the use of it? I mean, it's the thing. But, you know, if, okay, given that, I think there are at least 3 reasons why we want to be interested in this. And the first thing is, of course, that the cosmic web is the first manifestation of non-trivial structure formation. It's the first stage of structure development following the linear phase of evolution. This is the first time that we see real structures emerging in the universe. If you go much further, then you can get full collapse and get halos and in the end perhaps even galaxies. And then of course you don't have that much direct information and linkage to the initial conditions. In some cases you may even hope to identify indeed the global cosmological information contained in the cosmic web. Some of these features should contain information, and we do know that. For example, when you look at the voids, we now realize that, for example, the evolution of the shape or even if you take the average shape, assuming it is spherical, then you can apply the Alcock-Paczynski test, and you can basically infer from those things the global cosmological parameters. And of course, you could also try to look at other pieces of information. For example, alignments of galaxies with respect to filaments should also contain cosmological information. For the astronomy of things, perhaps the most interesting feature of the cosmic web is that it provides the environment in which galaxies are forming. And by now, looking at the properties of galaxies, there is the realization that the environment certainly has an enormous impact on the evolution and the formation of the galaxies. One of the factors is, for example, the accretion of mass, which is not isotropic, but is basically channeling in via the filamentary features to which they are usually attached. Other things is the dynamical impact via tidal fields on the rotation of the galaxies, etc., etc. So overall, it's an interesting thing to look. So what I actually want to look shortly is some of the characteristics, and then in particular discuss work on the analysis of the cosmic web and look at, you know, what are the properties of typical things like filaments and walls. How do they evolve in terms of length, diameter, and all these kind of things. And then in particular, today probably our focus on the phase space dynamics. And given time, I would like to say something about this adhesion work. So in terms of characteristics, what is the cosmic web? Well, first of all, on the basis of the analysis that we did, we're dissecting the cosmic web into its various morphological components. You can sort of ask yourself, how much, what fraction of mass or what fraction of volume is tied in with the different morphological aspects. So when you look in terms of mass, you find that more than 50%, around 50% of the mass of the universe is embedded in filaments. And it's the same for halos of galaxies, and as we found from analysis of the Eagle simulation, then when we also looked at galaxies, it's the same thing for galaxies. Around 50%, half of all the galaxies in the universe, are actually embedded in what structures that we call filaments. Notice, by the way, that also a certain fraction, around 15%, is lying in voids. So voids are absolutely not empty. They are underdense, and they certainly are populated. Of course, there's also quite some galaxies living in nodes, and those nodes, if you look at their volume, are of course a minor fraction of the whole universe. The voids take up 77%, so they're clearly underdense because they only have 50% of the halos and the mass. Filaments, 6%, while they contain 50% of the volume of these things. So if you then look actually at the density distribution, because that's one of the questions that's sometimes asked by my astronomy colleagues, why don't you just take a density cut? Right? These and these features are filaments, and that's about it. Well, here you see that that's actually not a very smart way of going around. Because if you take the filaments and you look at the density distribution in these features, and you take into account that this is a logarithmic scale, and you look at the PDF, you see that filaments are there over basically a scale from 100 up to 1,000 times the mean density of the universe. These guys, these underdense guys, are actually the guys, the tenuous tendrils that are living in those voids. While these guys, the extensions over here, are basically the very heavy filamentary extensions of the cluster nodes that you see over there, while a major part is actually around medium kind of densities, right? In between 1 and 10, that's where you find most of the mass in the filaments. If you then compare that to, for example, voids, you see that voids are sort of centered around 10th to 20%. That's exactly okay, right? So most of it is underdense, but also notice that this analysis gives that some of these voids are actually overdense. The reason for that is that this is based on an analysis that has some morphological features, and of course it looks at things like a landscape, like a mountain landscape. And in the mountain landscape there are the occasional lakes in the mountains. And they are, of course, with respect to the rest, overdense, but nonetheless they are local lakes. So those things, and of course if you then look at the nodes, some of them are, you know, sort of group-like, but here you have the heavy cluster-like. So that's the first major sort of inventory of these features and one of the rationales that you want to look at it. This is sort of an overall view. So in terms of characteristics, I would say there are 4 characteristics to which you should pay attention. First of all, of course, it's anisotropic structures. It's structures that are elongated or structures that are flattened. They dominate the outlook of the cosmic web. Very important, and I will get to that in the method that I'm going to discuss, is the multiscale nature of the cosmic web. The other thing is the asymmetry between overdense and underdense. While in the initial conditions, in the initial Gaussian field, it's 50-50 between underdense and overdense. Here you clearly see that most of the volume is in the voids, but they contain least of the mass. Yeah?
So how does the multiscale nature manifest itself in the previous figure that you showed?
Can I get back to that in the next slides? Because then I'm going to discuss actually the method that's underlying it, and then you will see where the numbers are coming from. Okay? And then the final last thing is the sort of topological features, that's topological aspect of the complex spatial connectivity. It's not a random distribution of filaments. It's not a random spatial distribution of walls. They are connected with each other in a particular way. And that's a sort of a topological aspect that needs to be understood too. If you want to understand then, or have an idea of what this means in terms of the structures that you see, this is one of the results of the analysis that we did. And what you see here is basically a slice through a simulation. And what you see in blue is the filaments. You asked about the multiscale thing. So you see this is a major artery. This is a small tendrils, etc. This method of basically classifying and tracing the structure is capable of taking this into account, that you have these major things, but also these minor things. I will explain later on how that goes. In that plot that I showed, everything that is blue, what you see here, is characterized as filamentary stuff. So when you looked at that blue line, you know, here's the dense stuff, but here is the very low dense stuff, right? So that's basically what I said with the multiscale nature. You see that the structure is extremely intricate, and when you look at this analysis, actually, so the technique that we used is coming from medical research. And at the talk that we had for some collaboration in computer science, and medical people were there from the university hospital, they thought that this was arteries. So you can be mistaken for that. I will show that actually this technique is coming from them. In terms of voids, I said, you know, the dichotomy between voids and the overdense regions. This is the reconstruction that we did with the adhesion approximation obtained from the 2-mass redshift survey. And basically what you see over here is 2 slices perpendicular to the local supercluster plane. The local supercluster plane is this and this. So this is 2 perpendicular views. What you see in red is the galaxies from the 2-mass galaxy redshift survey. And the stuff in green is basically the overdense stuff, the filaments and the walls, the membranes in the whole thing. And you see that actually the match is pretty good. It's very nice. It's actually the average the mean of 25 constraint realizations obtained from this analysis. And what you see very nicely is the structure in terms of voids in our local universe. So this is what we usually characterize as local void over here. And usually it has actually substructure. Usually the local void is taken as a huge thing and called the Tully void. But actually you see some substructure, microscopium, local void, and trans-Tully void. The fact that you have these... Basically, what we did, it's based on a Bayesian inference technique, Kaijin, from Francisco Kitara, who on the basis of the 2-mass galaxies reconstructs the initial Gaussian field. So then you have both the initial density field and the initial velocity field, and you feed this into, in this case, the adhesion approximation. So we use 25 of these inference constraint conditions, and then used it up with.
So you continually feed back to deal with the Rien space?
Yeah, in a sense it is. Yeah.
So you're taking a guess of initial condition, you move it forward and say that doesn't work?
No. That's the first step. It's the Bayesian inference technique. That's indeed what it is doing. So it basically does this feedback loop. So it's an enormous calculation. And then from this, in the end, you get, a range of realizations that are close to what you should have in the same way. And those fields we use in the adhesion. And then from that, we reconstruct the local cosmic web. And because there is some variation between the constraint realizations, we sort of take the mean, and then we get...
And how far out do you go?
To 150 megaparsec. This is only slightly more than 150, but this is the box.
150 across?
Yeah.
That's 75 in radius.
Yeah.
So, I mean, it's extremely interesting to try and have a full reconstruction of the shear field around this, and that automatically comes out of this thing.
Yeah. Yeah.
With all of those.
Yeah. In this case, of course, with adhesion, right? Yeah. Adhesion misses. Yeah. But we use specifically adhesion here because we were interested in the outline of the web and not, all the other structures. So this is a sort of a reconstruction of the real world, as is this. It's the same reconstruction, one of them, in more detail. This is the Perseus ridge that you see here. This was obtained by my student Johan Hidding, who's really keen on doing visualization things. And so what you see actually is also the imprint of the solution technique on the basis of spatial tessellations. That is a detail involved, but what you get is a beautiful three-dimensional rendering of our local universe. So here is the Perseus cluster region, here's the Perseus ridge, and you sort of see the depth of the structure. We are here in the front, and so you can study,
But if you're using adhesion, you aren't doing anything on masses.
No. So this
is like morphological.
This is like, this is like surface densities. But it's, it provides a beautiful view of the connectivity. So, coming now to the analysis tool that we used to analyze the cosmic web, this multiscale thing. To this end, we developed over the years, it started gradually some 10 years ago, and it has been sort of developed further and further and further, the tool Nexus MMF, and MMF is the name that you will find in the medical literature, multiscale morphology filter. And so we've translated this tool from that medical people use into something that we can use to analyze the cosmic web. So it identifies anisotropic features, but it does this on a range of scales. So where did we find this idea? Well, this idea came actually from something that exists in medical research, and it was developed in the 1990s. And the reasoning is pretty much the same. If you imagine in a hospital, a medical specialist has to study a high range of pictures, of photos, CT scans. Now, if you've looked for, a few dozen of pictures, you get tired. So you don't pay that much attention. But the point is, of course, that you have to look for something that is not in order. Imagine a lump, for example, in such a picture. If you have 1,000 of these things, how, as a medical specialist, are you go around this? So computer visualization people use or develop this tool for these medical specialists who use it to basically feed in their sequence of CT scans, and then the computer tells them, well, maybe you should have a look at this photo, and maybe this one and this one, but the other ones are not that interesting. And so, of course, what they look for is interesting, outstanding morphological features. If they would be interested in veins in your body, they would say that, but most of the time it involves something like a lump over here that should not be here. Now, you also see that the veins, the arteries in your body, are pretty much a multiscale branching kind of feature that we also see in the cosmic web. So they have the same challenge. The one advantage that they have is that their pictures have a much higher contrast, much larger dynamic range. But so they thought of this thing. The people involved were Florac, Sato, Franchi, and a whole range of people. And what they basically did is take the photos that were usually they are two-dimensional, and then translate this in a three-dimensional space, which they call scale space. We have to do the same thing, but we do that for basically a three-dimensional picture. So we get to a four-dimensional space in which one dimension is a filtering scale. Usually we use a Gaussian scale. And so what you do is you take your image and you filter it on a whole range of scales. In theory, from 0 to infinity. And subsequently, you're going to do a morphological analysis on each of the filter scales. So basically, it should be continuous. In there, you're going to look for features that are elongated, for features that are flattened, for features that are void-like or cluster-like. And subsequently, the idea is that you're going to look for the dominant ones over that range of scales. So imagine you're embedded in a filament, right? A big filament of 5 megaparsecs. Now, of course, when this is a uniform filament, if you are sitting at a scale of 1 megaparsec, you probably would get something that is not completely elongated. It would be more flattened because that scale is much smaller than the filament itself. By 5 megaparsecs, 4 to 5 megaparsecs, you get a feature that says, well, this is pretty much elongated. Then you have to start comparing which signal is most prominent. And that's where some of the artery the cookery comes in. You have to find criteria that says, well, that thing on 5 megaparsec, that's the dominant feature. Pick it out. And the stuff on 1 megaparsec is not so important. Or you could find, in the case of the voids, there you find that actually you find little elongated things at a scale of a fraction of a megaparsecs, while you don't see anything like it on a scale of 5 megaparsecs. So the technique then says, well, you should have a look on 0.1 megaparsec, that's where you find a filament. So that's what we do, and we translated this into basically the tool that we have. So it's in a sense, everything can be summarized in, you take convolutions with Gaussian filter scales, with Rn, the filter scale running from 0 to infinity, and you basically combine them all. That's your four-dimensional scale space, right? Now, what we did is not only do this for the density field or log of the density field, but we were interested in a range of physical quantities that are tied in with the cosmic web. Like Dick just asked, tidal shear or velocity shear. So we actually developed all of this for a range of these quantities: densities, the shear of the velocity field, shear of the tidal shear, the divergence of the density field, a range of these things. We basically got methods for each of them. So for example, here you see what was coming out is the log density field, while here we were looking more to the shear. So we have basically formalisms for each of these couple of things. Yeah?
So how does this method just described compare with standard feature extraction we use in computer vision, like edge detection?
That we didn't compare. We did compare it with some other techniques. There's a paper in the beginning of this year where we sort of compared it with other techniques that try to find filaments or stuff like that. And the agreement is there where it has to be. So we find filaments where some other people find them too in test sets. We didn't do a systematic comparison with that thing, because what you're talking about is basically a more topological related technique.
I think that, correct me if I'm wrong, but I think that they use discrete wavelengths for a lot of...
okay, right.
So I don't know how many filter banks you have, but if you do the differential of the filter banks, you know it's like you have a continuous wavelength field rather than a discrete wavelength field. So
yeah.
It is all of that. In fact, it's obviously complete.
Yeah, but in a sense that's this too. Yeah. No, but what you talk about edge detection is what in computer vision is usually called the morphological distinction. So we have another method, which I'm not discussing here, for finding voids, which is the watershed transform, and that's very much related to that field, right? That's if you talk to these computer vision people, that's what they are talking about when you do this. But it's not what I discuss here. So one thing that you have to do, of course, if you take the density field or the velocity field, it should be represented in a way that it really retains the signal of the cosmic web. So you cannot just arbitrarily go to some computer simulation and take it and then sort of first try to infer a density field on a grid or something like that, because that would basically lose most of the structure, the thin structure, the anisotropic structures in which you're interested. So what actually we feed in when we look at the galaxy survey or n-body particles is actually something that is based on something that we did a long time ago that's called the Delaunay tessellation field estimator. So we basically use adaptive Delaunay and Voronoi grids to sort of get local estimates of the density and then subsequently get a complete piecewise linear density field based on the interpolation on the Delaunay grid. So what you see here on the background, that's basically what's fed into this multiscale morphology filter. And you see it retains very nicely the kind of structures that you're interested in, right? So that's the density field, but at the same time, this method yields the velocity field. And you see the velocity field, the two zoom ins, you see that the velocity field is also very nicely following what you have, because you have a basically nice continuum of a velocity field. And that's what's fed into the analysis.
What are the imaginary points in the tessellation?
In this. In this case, it's only the particles of the n-body simulation. In the case you apply it to a galaxy survey, it's the galaxy positions. Right? So it's all the information that you have. And you try to optimally use it and not lose any information in sort of, filtering it towards predetermined grids or something like that. This is an adaptive grid. It does it itself. Right. Okay. Now, what we then do is basically filter it and determine the, for example, in density field, we look at the local variation of the density field, so it's geometric. You look at the Hessian, basically, of the local mass distribution. And of course, the shapes of that is determined by the eigenvalues. And the eigenvalues is basically what the story is about. The values of the eigenvalues is determining whether you have a blob, a more roundish thing, something that looks more elongated, or something that is more flattened. So that's what's determining basically the geometry and the morphology. That's at one scale, but you have to do this at all the scales. And then you compare the different scales of this thing, and you select out on what scale you get the dominant structure. So what you get is basically this. What you see on the background is the filaments, and the color is actually indicating on what scale the filament was selected, right? So, for example, the red ones, you see here is red filaments, and you see it's a very high density region, and that makes sense, right? That's a major filaments are near the clusters. But in the more low density regions, it's more blue, and you see that's a much smaller scale. So you get basically a complete multi-scale picture. And in the end, you get the census of your filaments, and the same for the walls, and you can compare the various things. Our favorite method is based on the log density field. Yeah?
So you define a filament as something with two large eigenvalues at one layer.
Yeah.
As long as in one particular layer it has two large eigenvalues.
Yes, and then you have to go through each of the scale space layers and determine where the dominant feature is, right? Where the elongation is strongest. And there we use these so-called filter banks, which these medical people use for their arteries and stuff like that. So there is some, cooking with filters and things combining, and then it says that's the dominant one.
So is it always easy to find the dominant maxima, or there are maybe multiple maxima?
So in principle, we can do the multiple ones because we have that information. But in the end, what I show here is the dominant ones, right? So here you see the log density field. The filaments are blue. But here is the velocity shear. And you see there is quite some correspondence. You see that the main guys are indeed found. But the velocity shear cannot recognize all the small scale stuff. It doesn't influence very much the flow field, which you do see in the log density field. So it's ideally you would like to use various methods to look at this. But you can find these things. So let me skip this one. And then look at what we get on the basis of this analysis. So in terms of evolution, and it's some examples of what we did. So here is the evolution of the filamentary network and the network of the walls, as a function of redshift. So this is a redshift of 2. This is us today. And you see that overall, the network is diminishing in length. That's because the filaments are merging and becoming, basically everything starts to be concentrated in dominant large filaments. That's actually a manifestation of the hierarchical buildup of structure. I will get back to that movie in a minute. And you see the same for the wall, for the walls. You see that the overall surface area occupied by walls is diminishing in time. So how should you see that? Well, here you have a movie of an n-body simulation. So here's basically the n-body simulation. This is the filamentary network, here at the redshift of 8.7. This is the membranes. And then we follow it up to today. And so the blue and the orange is this multiscale morphology filter Nexus stuff. So you see what's happening to the filaments. The filamentary network basically has a lot of the small filaments merging into larger and larger filaments. And in the end, what you see today is these dominant bridges surrounding large empty regions. And that you see at the same time that, you know, if you look at the same void, it's sort of surrounded by a couple of membranes, and some of these membranes are then coupled again to the filaments.
So what you used here is the eigenvalues of
yeah.
di, dj, and rho?
This is based on the log of the density field.
No, I know. What's the Hessian that you use for your lambdas?
The Hessian of the log of the density field in this case.
So I'm an advocate of Laplacian -2 of that. Depends upon the power spectrum, though. If you have something that's more merely scale invariant, and we don't do that. But that is the thing that is more closely aligned to the dynamics. So have you? I assume you checked that out because you check out everything. So do you see much difference?
Here this is the normal density field, and we did a couple of density fields. So this is the log 1 plus delta that gave. We actually found that this was nicest for us. So it's,
I'm a believer in.
But here, for example, if you're talking about the dynamically dominant features, we found that the velocity shear is giving us the nicest rendering of what you see, what is dominant.
Yeah. So what I'm talking about is essentially the tide.
That's this one. This is the tidal.
Okay, so it looks pretty morphologically
yeah.
equivalent. It's just a
yeah.
fuzziness.
Yeah. Yeah. So we in the end we often combine various of these things dependent on the kind of things that we want to do. But this is a log of the density field feature of this. Yeah. Because it's, it very much illustrates this nice thing of these small filaments in the beginning, and then you see them merging away into the larger features.
Yeah, I call it the configuration entropy. Everything's entropy around here, at least at one point.
Yeah. So that's when what I showed here, that basically if you see the, yeah?
So if you use length divided by volume, then there's a physical scale involved. So in some sense, this is showing two effects applied. One is that then how many filaments you have per volume. Another is like the size, the thickness.
Yeah.
Of the filament.
Yeah.
You entangle those two.
I'm coming to that in a moment, right? I'll show you some of the statistics and inventory. So this is the total filamentary network. The subsequent thing is a bit more tricky, because then we have the filamentary network, and we said, well, can we actually objectively define individual filaments in the sense of branching? So here you have a cluster, and then here you have an arm, and here you have an arm, and in the other direction you have an arm. So Marius Kapteyn, who developed this, and who wrote the code for this work, made a method that is sort of, taking the individual branches of this filamentary network, and then we left with a sort of a sample, a catalog of filaments, and on that we can sort of do statistical analysis, or at least get an impression. And you addressed the issue a moment ago. Here you see some of the results. Here actually you see basically this is the diameters of the filaments, but before I go to that, let me show you some of the variations. So here you see along typical filaments, so we selected some filaments, you see basically the linear density. So you project the density along the skeleton line. And then you walk along the filament, and it's, if you tell your astronomy colleagues, they're basically always thinking in terms of uniform tubes, and you say, no. Look at these things. There's quite a density variation along the filaments, and this is logarithmic. So you have variations dependent on what kind. Here it's a factor of 10, but sometimes it's even a factor of almost 50 to 100 in terms of density, because you have these big, heavy filaments sticking out of clusters. Then they disappear into a lower density area, and then they find a connection later on again. And you see, and you see halos along these things embedded, and it's clear there is quite a variation. You also see that there's quite a variation, of course, in mass. This is a dominant one, right? This is this big guy that also dominates the velocity shear. Here, it's a tenuous, small void one. In terms of diameter, so we basically took the perpendicular diameter to the basically the skeleton line of this thing, and you see the same thing. There's a variation over the length of the filaments in terms of diameters. You see, there's thick parts near the clusters, and then they become thinner again, and etc. You see the variations. Then, of course, you would like to put some of these things together and ask, is there something like characteristic radial profiles for the filaments? And here you see some of them. So here you see filaments that were, these are the guys that were picked up, the heavy ones in the scale space. And these are the smaller ones, 1 to 2. And you see these small ones, yeah, they have some density, but it's a factor of 5 times the average. And then they dip below the average density of the universe. They're tenuous things. These guys extend over the whole thing, these dominant things, right? They're extending out to huge distances. For the walls, well, they are much more tenuous features. So you see some of them extend out pretty far, but most of them dip pretty fast below the average density. So that's because their surface densities are low in comparison to the surface densities of the filaments. And it becomes even worse when you look at halos.
That is average along.
Yeah. 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 In terms of evolution, that's actually also an interesting question. So we saw that there is evolution in the filamentary network. We saw that there is a connection between filaments and walls. You may wonder what kind of connections and how does it evolve? And here you have actually an outlook on the sky as seen from 2 halos in a simulation, cosmogrid simulation. And it's just because this outlook on the sky gives you a sort of original view of what's going on. In this halo, you see that when it looks at the redshift of 3.7 and you look at the sky, you see this intricate network of filaments or walls. It's hard to distinguish. This is the projection on the sky. Now, one of the things that you should keep in mind, what would you see on the sky if you were positioned in a wall? You would see a circle, right? If you would live in a filament, you would see 2 hotspots in opposite directions. So keep that in mind from this point of view. So what you see here is an evolution from 3.7 to 1.6 to today. And you see that this web-like features start to merge. And by now, 1.7, you start to distinguish indeed sort of a planar configuration. The plane itself consists of several substructures, but it's clearly planar. In the plane, you start to see hotspots. Because in the plane, stuff is actually moving towards the filaments, what you see here. And in the end, you end up with, indeed, an imprint like this, with a clear filament. And you clearly see the connection, therefore, between the filaments and the walls. The network is evolving by itself. This is a more outspoken example, where you already in the beginning are embedded in a clearly defined wall, and as it evolves in the wall, you see that in the end, there's only 2 hotspots. So it's, all the mass in that wall, in the end, ended up in the dominating filament. So that's sort of what we see. So we see apparently mass moving from these structures towards other structures, more dominant structures. And the question is how? So here we have an inventory of, in various ways, of where is the stuff coming from. For example, in this case, we ask ourselves, imagine you are sitting today in a filament. where did all the stuff come from at a given redshift, right? Now, you see that, for example, in the case of a filament, so this is today's filament, you see that at a redshift of 2, already around 70% was at the time already in a filament. But it surely also got a lot from the green stuff, which is the walls, right? So around 30%, 25 to 30% of the mass that you find nowadays in filaments at a redshift of 2 was in a wall. And, you know, there's nothing coming from clusters. Clusters, you clearly see what's going on. Clusters is the black line. So today, everything, of course, is in clusters. But as you see, most of the stuff in clusters nowadays was transported through the web and came from filaments. Almost 85% at a redshift of around 2 was in clusters, or was in filaments at a redshift of 2. So you see clearly the motions in the grid. You can also turn around the question and say, well, if I'm at a redshift of 2, where are you going to be at a redshift of 0, for example? So you see all the stuff here in filaments was actually diminishing. Why? Because it's moving towards clusters, right? And the same is for walls. And then, for example, if you look at voids, you see that most of the stuff from voids is first moving into walls, then towards filaments, while, of course, the voids themselves are constantly losing mass, they are evacuating. So here you see sort of the quantitative impression of what you are, you know, thinking of in how these things happen. You could even turn it around in a more visual way. And for example, here you see this is filaments, and here filaments at a redshift of 0, here a redshift of 2. And the color at a redshift of 2 tells you this was in filaments at a redshift of 2. What's in red at a redshift means that filament stuff at a redshift of 2 ended up in a cluster. And you know, this stuff ended up in filaments, and at the boundaries there is some crosstalk between the walls and the filaments, but you sort of get the real picture. While here you are asking yourself, you know, today, this is the filamentary network of today, where did all the stuff come from? So the blue colored things at a redshift of 2 were already in filaments, but the green stuff was in walls, and there is at the edges even some crosstalk between the clusters and the filaments, so it's moving back and forth. So you can ask yourself sort of that game. You can also do it with voids, and you see that, you know, basically everything that's left in voids today was in voids a long time ago.
So can I just take a step back to try to understand what it is that I'm looking at? So you're defining these beautiful maps in terms of basically lambdas.
Yeah.
And then the lambdas have been chosen at some hierarchical filtering bang.
Yeah.
So that this point here with its lambdas has a different filter maybe than this one over here. And therefore you need the algorithm to say who's prominent and who is not. And with peaks, peak patches, etc., that's kind of obvious what's done in class. It is not so obvious from the point, I mean, maybe it's obvious from the brain's point of view. I can't actually believe it is. But, I mean, it seems like, you know, there's a lot of swamp there in the algorithmic definition of what is defining a prominence. So, for example, I can say, you know, my prominence concept will be something that's going to light up, which means that it's going to go more towards the condensed entities and away from the sort of smooth operation net. So what is the algorithm of prominence?
it's not a dynamic criterion when you talk about the density field, it's a morphological criterion. Yeah. So it basically says, in terms of the density, if you're living in a filament, how strong is the, how strong is the filament? What is basically the strongest filament on a certain scale?
But is that looking for specific points and giving a filter scale? So one of the things that, and I know you're an expert on this as well, is prominent saddle points as well as peaks. And so the saddles have been used to try to identify.
Yeah, that's topology. What? That is basically the topology of, that's not this method. That's what I call what I mentioned, the watershed technique. Is basically doing that exactly. It looks for the topological connections via the saddles.
Because it's got a pseudo-flow.
Yeah.
Well, anyway, we'll talk about this later. I think
yeah.
This is a really interesting question because I got into geographical, I guess it's topography, because usually they want to get rid of high-frequency things and look for what the eye would say is prominent.
Yeah. to
what you call prominent is, well, it's obviously depends how closely you're looking at something.
Well, so it's exactly what you say, and that's what basically these medical people did, right? They see these images, and they are these visualization experts, ask themselves, if you look at these pictures, what is the human eye picking up? Right. And that's what they translated into this scale space bank of filters, and which we basically copied. Yeah. And I mean, the thing is that when we compare it to the simulations, etc., and we look at the filaments that we have, then you see, yes, I can recognize these guys. You know, it picks up this filament, and I recognize, my eye sees it too. So that's sort of the, but it is morphological in that sense, and it doesn't have this topological thing of on the basis Morse theory, etc. That's the watershed stuff and spine web, and that's another method that we did. Okay, so what you see here then, Dick, is basically so the evolution of redshift 2. You wonder what's going, and that's this morphological distinction of the cosmic web, and a redshift 0, but there is not per se a dynamical connection. The only thing is you do it for a redshift of 2 and you do it for a redshift of 0. And you wonder, you have the particles and you wonder where did you come from. Does that answer the question? So, in terms of filaments and the filament population, let me then, well, I have various plots, but let me go through, show you a few ones. So you can sort of make a mass plot, a mass spectrum of filaments, and ask yourself, how is it evolving? So here you see basically what's going on. This is for different redshifts, the mass spectrum of filaments. So it's the entire mass contained in the filaments. And what you see is that on the small scale end, there is decrease. On the large scale end, you see its increase. And that's, of course, directly manifesting what you saw in the movie, basically, of the evolving network. The small-scale filaments are basically merging into the larger ones. Right? So this is direct manifestation of the hierarchical evolution of the filamentary network. So you can do various things in terms of, for example, lengths of the filaments in areas of the walls. And the only thing that I can say here, you can read this in the paper in detail, is that you clearly see that the small-scale filaments are merging into the large-scale filaments, but you don't see it that clearly for the walls, because actually a lot of the small-scale walls is just running into the filaments. So they are getting, they lost. That's basically it. So there is some distinction over there. So, yeah? Yeah. So let me then go to something that is interesting for astronomers, and that's what's the population in these various objects. And so here, this is basically based on halos, but we basically determined the mass function, the mass spectrum of the halos. And what you see is that clearly, for example, if you look in the filaments, they have a regular distribution, mass distribution that is very much akin to a Schechter-like function. The voids too, but they are much less numerous, and they are much more small objects, right? Massive galaxies or massive halos you don't find there. It's the same with the walls. They are sort of halfway in. And that, in practice, has immediate ramifications. So here you see a wall. And if you look at the colored dots are basically the population of halos. And you see the mass, the color represents the mass. Blue is tiny, 10 to the 10. These are the heavy guys. This is in between. And you see that in between, that's what mostly is populating the filaments. But the walls are only very small galaxies. And that's one of the reasons why in galaxy surveys, you hardly can find them. Because first of all, their surface density is extremely low. But on top of that, if you do a magnitude-limited survey of galaxies, nearly all of your population of galaxies in walls will drop out. So you can't see them in the survey. So that makes the filaments much more dominant because you can't see the walls because they're populated by tiny guys. Right? So this is certainly for astronomy kind of purposes interesting. I have 5 more minutes? Okay, so I'm gonna skip this. And I'm going to something that shortly what I've been doing lately with Job Veldbrugge, a former student of mine. And that's looking into phase space evolution, so dynamics of the cosmic web. And it's since some 7 or 8 years that on the basis of work of Sergei Shandarin, Tomei Bell, and Mark Neyring, people started to see that actually phase space is containing a lot of interesting information about the cosmic web. Here you see basically a phase space evolution in 1 dimension, and you see what's going on. Around the place where a structure is forming, you basically get a multi-stream field, right? So, gradually you get the evolution, and you see that at a certain moment here, streams coming from different sides are passing each other, and then you get a virialization process, and you get structures like this. When you look at that, you get a very sharp outline of the density field. They realize that. It's much, much better than any of the pure density-based things. Because basically what you should do is sum over the different streams that are meeting at one different location. So if you look, for example, at this thing and then look at the integral along this line, you get a spiky distribution. And they pick that up. You can pick that up. So this phase space thing is actually mighty interesting. So if this, you would see, is sort of your 6-dimensional, a 3-dimensional sheet in 6-dimensional space, what the dynamical evolution basically is a wrapping of this phase space sheet. And what you see on the sky or in your plot is basically this, is this Eulerian space. But you basically see just the projection of the faults, and you get all these fault lines, and they basically are the regions where different streams are meeting each other. So the realization came that by looking at this, you could actually get a more dynamically motivated characterization of the cosmic web. You could say, for example, there where streams are meeting for the first time in 3 dimensions, you would get, once they've passed, 3 streams at one location. If you have a filament, it's 5 streams because it comes from the other direction too. And actually you can look at it and get enormous amounts of streams in particular locations. So this is from work from Tomei Bell and Oliver Hahn. And they sort of characterized it on the basis of the multistream field. So, if you then want to look at the evolution of the cosmic web, and in particular in cosmologies that do not have a lot of small-scale power, you get very nice rendering of what's happening. And here is a simulation that I got from Raoul Angulo and Oliver Hahn of a warm-dark matter simulation of the cosmic web. And what I want to point you out is this density field is predicated on this phase-space structure. And you see how razor sharp these features are. And you see these sharp images, edges, are actually what's called caustics. That's where the density reaches infinity, because things are just meeting up at that location. And look, for example, at these high-density nodes. It's like, you know, wrapping paper or something like that. And it's basically the evolution of the multi-stream structure of this cosmic web. So, can we do something more than running a simulation and make beautiful density maps? So can we infer more information from this? And yes, we can. The thing is, you can actually look in this structure, and for example, by looking at phase space, but look in phase space not in terms of space and momentum, but look in terms of the initial Lagrangian coordinate and the Eulerian coordinate. So what you get in the multi-stream regions is basically mass elements from different locations are basically lining up in one particular location. And you can actually, on the basis of the deformation tensor, that is the deformation of the density field, identify where this is going to happen. Actually, the good old Soldovich is exactly who predicted this. So this is actually from a paper that we wrote, Johan Hidding and Sergei Shandarin and myself, in the two-dimensional situation. This is Lagrangian space, and the contours are the deformation, are the first eigenvalue of the deformation tensor. And the first eigenvalue determines when, for the first time, you're going to collapse in a wall. This is in Lagrangian space. So here you see, for example, when a contour that is at one particular time going to collapse. And the question is, where is it going to collapse? Well, it's going to collapse along one particular line, and that's called an A3 line. All this is mathematics of so-called catastrophe theory, which goes back to people like René Thom and Arnold, the Russian mathematician. They identified the various classes of wrappings that you could get in the various caustics that you could get. In terms of Eulerian space, the first one that you will get is everything is basically ending up into a pancake. That was the good old pancake theory. But at the edges, you get basically what we call cusps. And they are actually wrappings of the wrapping. Exactly what you saw in the movie. So, in view of the time, let me skip the details and just report what we did. So we basically did the whole analysis of Arnold again, but inferred practically implementable conditions for the various caustics that you would get in this space. So where are going to be these pancakes and where are going to be these things? Everything predicated on the deformation tensor. You just look for the caustics, the various caustics. And what you see here, this movie, is basically for a cold dark matter field. Oh. Is it moving? Yeah. These would actually be dynamically the walls. It's called the A3 membranes. But we did the whole thing. Basically, Job rewrote everything and inferred the conditions for any dimensional space of caustics. And everything depends on the eigenvalue of the deformation tensor. But not only that, it also depends very much, the geometry, on the eigenvector. And that's usually skipped. People only talk about this, they don't talk about that. But that's actually what's defining the outline. And I just want to present what we find in this sense. So you basically did the whole Arnold caustic thing in 3 dimensions. And you can actually identify the filaments are basically swallowtail caustics, A4. I will soon show you that this is really true. So it's mathematics, but it's really very much what you see in the cosmic web. Let me show it for 2D. This is at 2 different smoothing scales. The Lagrangian space, the contours, is the first deformation tensor eigenvalue. And the lines are these A3 lines, and these dots are basically the A4 nodes. They would become the nodes. Projecting them into a Larian space, you see what they do. So the lines are actually indeed lying on top of the density contours. So you see that what is a filament here in density field indeed is this A3 line. And you see the nodes here, that's where the clusters are. They are the A4s. This is in 2D, so it really shows it works. So this is actually what we did last week. And so what you get here is a cold dark matter simulation. In there we determined the deformation field. In red you get the A3 caustics. They are the walls. The blue guys are the A4 lines. They are part of the filaments. Remember that they are only predicated on one eigenvalue, collapse in one direction. So they are basically the lines that are shared between different walls. The yellow ones are the D4 ones. And the D4 caustics, the umbilics they're called, demand collapse in 2 directions, 2 eigenvalues. And here you see that network. So you see the filaments is both D4 and A4, and you see this thing. If you also see on the background sort of the density contours. And if you see, it really follows it to some thing. Here you see it again. I'm going back and so look at this. So you have the membranes, and now I put the density field on top of it, and you see it's really following the filaments exactly like what you see in the density field. So this is just a progress report of what we're doing now. This is a more dynamically predicated method. So this really looks at the dynamics simply on the basis of Seldovich. But Seldovich seems to be able to follow in real sophisticated detail the cosmic web, much better even than what I had imagined. So I think I should stop over here. Thank you.